So next we're going to talk now about variable speed CMG. We just wrapped up reaction wheels. We showed how we can use a classic Lyapunov function that we had earlier, just modify what the system is, and we solve for sets of motor torques. And if we have redundant ones, there's an infinity of answers, and also how to implement it, right? Talking about how often do you have to update those things. Now with variable speed CMG, we have one of these devices. We actually have two, we can torque about the spin axis, like it just acting like a reaction wheel, and we can also torque about the gimbal axis, making the spinning wheel change its orientation with respect to the body. And so we have two modes that we can control torques now per device, which is kind of cool. We do assume full states feedback again, so we know the attitude, star tracker, we know our rates, rate gyros, you have on board, all the classic same stuff. The biggest difference is now the actuation. And when we develop this, we won't see this at the beginning, not today, but later next week. At some point, we have a lot of options because we tend to have 4 of these devices, 2 control inputs. So with reaction wheels, you have 3 or 4. Rarely do you have more than 4, but that is possible. Here we have clusters of 4 CMGs where I get torques from gimbaling, but I can also increase or decrease the wheel speed, which gives me different torques. So I get 8 control knobs for a 3-dimensional problem. We will have a lot of options. But that's good, because there's a lot of challenges. There's gimbal lock, there's all these elliptic and hyperbolic singularities, and all the other stuff that appears. So ideally, we would like to use these things as CMGs. Remember the equations of motion that we had, all that stuff? There was that one term that had to do with the wheel speed times the gimbal rate. And that was a huge gyroscopic term. And in fact, that term appears acting on the GT axis. So the CMGs take advantage of that as you gimbal this wheel, it's going to create a huge gyroscopic term. And unlike the reaction wheel controls, which have no other option but to feedback compensate for their own, their wheels are rotating because the spacecraft is rotating. And you just have to compensate and have big enough torques to be able to compensate. With the CMGs, it's going to be different. We're going, man, that's the sweet spot. That's what we want to use. So we will want to come up with controls that takes advantage of that. But that was wheel speed times gamma dot, not gamma double dot. So how do I come up with controls for the gimbal motors to do all this These are the questions we have to answer now as we dig into it, okay? And then, as I said, there will be singularities, and we'll probably get into those today, otherwise next week early on, that we have to talk about. So nothing's for free, as in life, We get great torques, we put in a little input, and you get a huge torque out. Isn't that cool? The drawbacks are tons more math, much more expensive devices. The calibration, you're spinning at very high rates all the time. And there are singularities. So any momentum exchange device, if you put an external torque on it, it will hit a limit at some point. Wheels will saturate. You can't spin any faster to hold that attitude, and then it starts tumbling. CMGs will get gimbal lock, and you will see what that means mathematically. So we want to develop a attitude tracking control problem that now, instead of using just an external torque like we did in the first homework, or now we just showed you how to use reaction wheels or sets of reaction wheels, we want to expand that and use sets of VS-CMG devices. How do we do that? Well, we start out with a quick thing. I want to remind everybody, the inertia tensor I'm going to show you is going to be of the spacecraft hub. That's the rigid part, right? And then everything else, the CMGs. J's were the inertias of the gimbal plus the inertias of the wheel. We could kind of combine those in the math as you've been developing. And these are just the axes of the G-frame. The outer product give you the projection planes we need. So we can write this way. The tracking errors, it's again a tracking problem, so I need the body relative to reference, and then del omega is Bn minus omega Rn, and del omega really is omega B relative to R. And it would be in B-frame components evaluated in the kinematics. Same as before, we're going to throw in a tracking, the Lyapunov function, the del omega and the sigmas that we had. That's cool. And then we differentiate. And so while V is a scalar, so we're just taking a time derivative, the scalar is a product of really matrix math or vector dot products that create a scalar. So if the sigmas are just matrices, so that's just a time derivative there. There's no B-frame derivative of sigma. It's just a DDT. They're just three components, right? But the first term, del omega, is omega minus omega r. Those are all vectors expressed in the matrix frame. So with respect to which frame do we differentiate? We still pick the body frame like we did before. But what's new now, too, is whereas with the reaction wheels, yes, the wheels are spinning relative to the body, but the mass distribution didn't change if the wheels are balanced, right? And as it rotates, the inertia is always the same. That's no longer the case now, because as we gimbal, that spinning disk is going to move, and that's most definitely going to change the mass distribution. So there will be a body frame derivative of that inertia tensor. So that's going to be a new term we have not seen before that we have to deal with. If we do that, so here, taking the body frame derivative of this inertia tensor, we can take advantage of that. This is a nice way to write that time-varying part of the spacecraft inertia, because the GG parts are constant, right? That part is locked in. So that's always going to be that, and its derivative in the body will just vanish. That's cool. So that leaves you with chain rule with the GS, GT, and GT, GS transposes. And then using these body frame derivatives, which we looked at earlier when we derived the equations of motion, that was pretty straightforward. We had that. You can plug it in, and so that gives you now this derivative once you do all these differentiations. As before, this gives us a V dot. We would have to plug it in, but put this in here. And we're going to set it equal to something negative semi-definite for the system. But because we will be factoring out rates again, this is a second order system, so my Lyapunov function in terms of states and rates, the V dot, the trick we can use, because this is a scalar equation, you cannot solve a scalar for a vector set or a matrix set. So factoring out this matrix, del omega transpose, on both sides of what we got when we differentiated V and what we're prescribing V dot to be, I can then say again that this bracketed term must be equal to minus P del omega, right? Same argument over and over again. And that leads to this stability condition. This is all the stuff we had before. This is a new term we have to compensate for or incorporate the body frame derivative of that inertia tensor. Otherwise, it's very, very similar. So now I'm going to outline. I think at some point I'm asking you actually to derive this yourself. So you'll be filling in the blanks on your own when you do this. So that's the condition. Now, how do we come up with a control law to do this? Well, let's see what happens. We know all these terms. This one, I showed you the answer, and you should derive this yourself there. So we'd have to plug that into here. This part, we've seen this in our earlier controls, del omega, right? The B frame derivative of omega is going to be what in the end? Omega dot, right? Yeah, that cross product term drops out. But the B frame derivative of omega Rn is not omega Rn dot. There's an extra cross product term that appears, right? So with the transport theorem. So we've done that several times, but that's what you'd have to plug in here. So once you have this times this inertia tensor, so you notice we used here I, the total inertia. So in that Lyapunov function, I is not just a constant anymore, but it is what it is. But the convenience is I will have an I times omega dot, which means I can plug in my equations of motion. And here, these are actually convenient, written out this way, because I have everything that I need to directly plug it in for n variable speed CMGs, right? This is the version where the GS, GT were nothing but the n 3 by n's stacks of all the gimbal spin, transverse, and gimbal axes, gimbal frame, spin, transverse, gimbal axes. So that's cool. We can plug that in. Now, what were those things? So that's were these, and all these taus is all of this stuff. Julian is giving me an evil look. Yes, that's all, right? In quotes, all that we have to do. And this is the new stability condition. to achieve these closed loop dynamics, which will guarantee a negative semi-definite V dot. And you could do Mukherjee chain again, or Lazard's invariance principle, and take, and prove this is like before, it's going to be asymptotically stabilizing if we can satisfy all these conditions, But before we had something a lot simpler, Don't you miss already the days of reaction wheels? That was the easy time where all of a sudden it's like, yeah, now instead of U, we have GS times U and one extra term, and that was it. Now we get this stuff. So how do we make sense of this? I've already started to make sense of this here. If you're looking at this condition, before we ended up with, you plugged all this in and it was 0 was equal to US plus K sigma plus other stuff, and you would find it. Here you can find, these are the things that should look very familiar. This line, whoa. Yeah, that's fine. This is what we had before with the reaction wheels. There was also some compensation for the reaction wheel gyroscopics. So just like with reaction wheels, we had that in our LR part 2. So as the wheel is spinning, and if I'm holding a constant gimbal rate, as the spacecraft tumbles, you will have some gyroscopics. But there's nothing I can do about that, because that's, I can't control the gyroscopics because it's dictated by the spacecraft tumble. That's what I want to, it's not something I can prescribe a tumble. So they're there. So that's basically the right-hand side looks an awful lot like what we had with the reaction wheel feedback control. But the left-hand side was just GS times US. And now we have this mess. So what do we recognize? Well, here you go. This is your GS times US. If we have no gimbaling going on, this is the stuff that depends on gimbal acceleration. All of this stuff is everything that depends on gimbal rate. That's why I took it all over to the left-hand side. And this is the stuff in the wheel acceleration. So this is the GS times IWS times big omega dot that we had with the reaction wheel control, just rewritten out as a summation versus a matrix projection stuff. That's it. Because we're gimbaling, we get all these extra things. And that's really how we should look at this. So before we just had the wheel accelerations and thus the motor torque, if you put it in the motor torque form, to figure out how do we generate the right-hand side. Now we have wheel accelerations, we have gimbal accelerations and gimbal rates. Now of course gimbal acceleration and gimbal rates you cannot individually prescribe. That doesn't make sense. Don't accelerate but keep going faster. That doesn't, it doesn't work. So we'll have to pick one of them. So you could just take all of the gimbal rates over to the right-hand side, and I'll show that in a second. And then we could plug in motor torques and treat it just like everything else. But what happens then? Here's that term, wheel speed times gimbal rate. And that wheel speed is going to be huge for a CMG. So if you just want to feedback compensate for that, good luck, to get that to work. So that's going to be the problem. So instead of using accelerations to get motor torques, what we will see is we will have to kind of make some approximation here, and we will actually use gimbal rates as our control variable, because we want to exploit the CMG gyroscopic torque. This is what I want to take advantage of. This is all the other stuff that happens, and we keep that because we're dealing with a variable speed CMG. I want to include an answer that I could be going 10,000 RPM and then change the speed down through 0 to minus 10,000 RPM. And my equation should always hold. Many CMG papers, variable speed CMG, always talk about you're spinning at 5,000 RPM, 8,000, 10,000 RPM nominally, and then you vary a little bit around it. But if you reconfigure, and you'll see with the null space motions, we change wheel speeds quite a bit sometimes. It would be interesting actually to see what happens, because as the wheel speeds go through 0, what happens to my CMG mode? If big omega becomes 0, and you gimbal something that's not spinning, you're not going to get any gyroscopics. So all of a sudden you lose one of these big things that you think is going to give you torque. Fortunately, we still have this, right? So we will still have controllability. And the other thing to keep in mind with the CMGs or the VIA CMGs is this stuff is acting on the GT axis. The wheel the reaction wheel mode is acting on the GS axis. Is it possible for GT and GS to be equal? No, right? They're defined to be orthogonal from each other, right? There's a gimbal, there's a spin axis, there's a transverse. So if I lose controllability about this one, then the spin axes at least will all be still there, but this one can't directly compensate for that one not working. So you need other wheels. This is why we have 4 in a pyramid kind of configuration. And we'll talk about singularities of that can occur. But this makes sense? This is a ton of algebra that you get here, but it's written out in the most general form that allows you to take wheel speeds that don't have to be high, they can even go slow. But then you're going to have issues, of course, with this is going to become a weak term, and this may not be ignorable. So it's a matter of bookkeeping in the end. And so what I did is I just took chunks of stuff and gave it labels to kind of keep track of this. So what we have is D0, that's really the stuff that depends on, that's the reaction wheel mode. The GS, IWS, and you see that in a moment. These are all the things that depended on gimbal rate, D1, 2, 3, and 4, and the B matrix is the one that depended on gimbal acceleration. So I've broken those things out. And what's different here is the D1, you can see it has everything with the inertia is about the spin axis. D2 is inertia about the transverse. 3 inertia is about G, and then D4 had some differences in inertias. I came in. I think that was the reasoning for my ordering. So all of these Ds I can actually combine as well, because all of them are impacted by gimbal rate. There was gimbal rate times all those terms that we were seeing, right? I mean, there's quite a few of them. So the way that works out, one of them had to be a negative, just the way the math worked out, but the rest of them were positive as they are defined. And if you do that, then all of a sudden, all that complicated mess we saw, we can rewrite now in a much more compact way. It's the same algebra, so we're kind of just cheating in a way, that just going, all this complication, you over there, you 3, I'm calling you Bob, and you 4 over there, I'm calling you Juliet, and somehow now I've made it simpler. It's like, no, you just relabeled it. But relabeling is a powerful tool, because to me at least, with this complex math, it helps me group and go, okay, what is the stuff that matters? And everything else that doesn't, I can put to a side and deal with in an abstract way. So this is our new stability constraint that we have. This right-hand side is really what we had before with the reaction wheel motor torque. This is the required torque, LR, that we must produce onto the body. So therefore, minus LR must be produced onto the VSCMG, right? Newton's laws were equal and opposite reactions. So right now we still have accelerations, gimbal acceleration, and gimbal rates in there. I'm going to have to think about how we're going to do this. This is for the tracking control. Like with rigid body attitude control, we developed the tracking control and had omega R dot, cross products. We also had to maybe feedback on omega tilde I omega, because it didn't just cancel out, or there was a trick with we could feedback on omega R tilde I omega that we showed, but there was always the tracking was always more complicated. If you do the same thing over from scratch just for a regulation problem, so then your control is drive sigma Bn to 0, not Br, right? Things simplify. And I'm showing you the answers just if we did a regulation driving everything to rest at the origin, MRP-wise. Then you go through the whole stuff, and this becomes that control constraint. The right-hand side looks a hell of a lot simpler. I'm doing regulation, so I actually took advantage that omega transpose, omega tilde, I omega drops out. I'm not feedback compensating for it here. It becomes much simpler. And all of this should be a bold L. This becomes the required torque I must produce onto the system, the VSCMG system. And then the left-hand side just becomes this. So I still have my reaction wheel mode, my gimbal acceleration components, and this is everything dependent on gimbal rate. You can define, it takes less Ds. D0 is always the reaction wheel part. B is the gimbal acceleration. But now I only have a D1 and a D2. So you can rewrite this in a way that looks exactly the same. Okay? So as before, regulation makes your life easier. tracking just gives you the full answer and better convergence, that you're going to have. So, I mean, as in always in life, if you're tracking a time-varying signal, but it's moving really, really slowly, the attitude is only increasing, 1 degree per day, you could put a regulation control on that, and it would kind of keep it pretty darn close without having to have all the other stuff. So sometimes you see people use, regulation on tracking if the tracking is really slow. But this is the general stuff we've done. So same formula, same conditions. I mean, it's different things that go into D, but it's the same groupings that we're dealing with. So it's fundamentally the same structural challenges of how do we now come up with a control law.